So today's keynote speaker is Dusan Keres, and he is from University of California, San Diego. We have a distinct San Diego connection with our keynote speakers this week. I guess that's the place to be if you're studying how gas flows into galaxies. And following his talk, we're going to have a panel discussion, including Avishai Deckel, Gwen Rudy, Freke van der Voort, and Filippo Fraternali. So I'm very interested to hear what the panel has to say about these questions. So I'm going to now cede the screen to Dusan, and he can get started on his talk.
Well, I would just like to thank Jess, Ben, Cameron, and Mark for organizing this great meeting. It's been really inspirational and discussions are great. I've been mostly lurking while making breakfast and things like that, but those were excellent and all the discussions were super interesting. And as Mark mentioned, I'll just continue with gassing falling into San Diego and following talk by Kate on nice observational results. I will mostly, I would say 90% cover simulation results and mention some related theoretical work and occasionally some observations. And I'm just going to give a brief outline before I go into details. So I'm just going to shortly pedagogically motivate gas infall and then talk about cold and hot mode accretion. Those were the simple times before we started worrying about feedback. Then I'll talk about what feedback does to this inflowing gas and how inflow and outflow might interact. It's actually kind of weird to talk about inflow and not go into both kind of flows. And it's going to lead a little bit into galactic recycling. And then towards the end, I will try to discuss how gas actually joins the galaxy, of the sense of co-rotation we start seeing in inflowing gas, both in theory and observation. And I'll touch at the end on these issues of vertical and parallel accretion and flow of gas through the galaxy. Those will be kind of more detailed stuff at the very end. All right, so one thing that kind of puzzles me and probably most of us here is why and how is the universe forming stars actively over all cosmic times we can observe, from earliest redshift 7, 8 to present time. Star formation activity of universe is pretty high. I mean, it dropped by maybe order of magnitude since redshift of 2, but galaxies are still cranking gas into stars. And kind of related question is what brings and what is the fuel for this cosmic star formation? And the related topic is how is the galaxy connected to the broader network of gas that's distributed throughout the universe. So one thing to note here is that even though star formation activity peaked about redshift of 2 per unit volume of the universe, most of the stellar mass in the universe form after that. About 70–80% of mass actually form after redshift of 2. It just universe kind of slowly started cranking down gas into stars at the lower rate, but there's a lot of time since then. So first thing, you might wonder if the gas available in galaxies can form all of these stars. And we know that stars form in molecular gas, and molecular gas has pretty short consumption timescales, definitely much shorter than the age of the universe, typically 1 to 2 gigayears, depending on the epoch. So molecular gas, doesn't matter how much there is, it's a transient phase. It's just going to quickly spend it and form stars or do something to it. Well, the other bigger reservoir that sits in the galaxies is atomic gas. And at redshift 0, we like to observe this atomic gas in emission, but at high redshift, most of the atomic gas that we see in the universe actually sits in them Lyman alpha absorbers. And the plot here on the right shows the density of Lyman alpha absorbers in this critical density unit as a function of redshift. And you see that this density is roughly flat between 0 and maybe 2, and then it increases maybe by 50% or factor of 2 towards higher redshift. But when you compare it to the stellar mass density in the universe at the present time, which is shown here as this star going out of the plot, and that's roughly, it's not fully to scale. You see that there was never enough gas sitting in the galaxies to produce this many stars. And most of the stars, furthermore, form after redshift of 2. So at redshift of 2, there is only a tiny fraction of available fuel to form this many stars by present time. So from these simple considerations, we know that globally, some sort of gas inflow from the ionized intergalactic medium needs to supply galaxies to form stars over all cosmic times. And we've been studying this issue mostly through simulations in the past few decades, and we found a couple of basic things about this gas inflow. There are significant differences how gas actually is being accreted in early times at high redshift and in lower mass halos versus late type galaxies. So in general, when galaxy halo is smaller than a few times 10 to the 11 solar masses, from simulations, we found that gas infalls into the galaxies or very close to the galaxies via cold filaments that are not strongly heated to the virial temperature of the halo. And at high redshift, this cosmological inflow tends to be of order of 10,000 degrees Kelvin, while typical virial temperatures of halos at redshifts 2 or 3 of L star, usually lower galaxies, it's a million degrees Kelvin. So these phases are well distinguished. So shock heated gas, it's roughly a million, cold gas is roughly 10,000. And this type of accretion, where you just don't really care so much about the virial temperature of the halo and you go straight to the galaxy, we termed cold mode accretion 15-20 years ago. And this cold mode accretion is efficient because you can directly fall onto the center part of the halo. So the rates are roughly determined by the growth of structure of the universe. So the halo growth rate within a factor of 2 or 3 can give you accretion rate as well. And this was also recognized very early, but wasn't really explained how it works. So in very early semi-analytic models, we recognize that something will happen when cooling time at the virial radius is shorter than free-fall time. That something will happen with the stability of potentially hot gas in halo. And in semi-analytic models, this will be the gas that can just go straight to the galaxy, but it didn't quite explain what will happen with such gas. Clarification came with Burboin and Deckel's work in early 2000s, and then Deckel and Burboin that look into these issues in much more detail. And they found that cooling time needs to be longer than compression time after the shock if you want to have stable shock in the halo. And they calculated conditions for this to happen for the halos and found that only halos that are a couple of times 10 to the 11 solar masses can have stable shock. If you're a lower mass, then your shock will be unstable and crazy things might happen in halos. Situation might be a little bit more complicated in reality because of these filaments. So you might have stable shock in between where density is super low and you can still stream to the center, but we'll get to this in a second. Here, I just want to say that this is typical for high redshift galaxies. So this is 10 to 11 solar mass halo at redshift 3. This is 3 to 4 times 10 to 11 solar mass halo at redshift 3 also from Agartz. It's a beautiful illustration showing cold infalling gas very close to the galaxy, metal enriched gas stripped mostly from the satellite and perhaps a little bit of outflow around the galaxy, and some of the hot mediums starting to develop in low density regions around. When you go to lower redshift, things are a little bit more complicated because filaments get a little bit warmer. The density of IgM is lower, so you tend to be heated to slightly higher temperature. The typical at the given halo mass, your lower sigma peak, so you tend to sit in thicker, more isolated filament. And the virial temperature of the halo at the given mass goes down. So cold mode exists, and you can find the shock stability criteria in low mass halos even at later time, but it's not as well defined. And when you go to really low mass halo, then you jump to the other side of the cooling curve and you might switch to hot mode in the lowest mass halos. I just wanted to illustrate this by this redshift 1 image here that still shows some sort of infall, but it's not as cleanly filamentary, and the hot and cold gas are not as distinct anymore in temperatures. So kind of looking for the clean distinction between cold and hot mode in lower mass halos. At the present time, it would be difficult. So when you go to higher mass halos, things change. So infall is mostly cold in halos below a few times 10 to 11 solar masses, but when you go to higher mass halos, oftentimes halo starts being dominated by the hot gas. So this is illustrated here in this older work by Osphere that plotted fraction of the halo material that it's infalling in blue as cold and red as hot. And the lower panel shows this fraction at 0.2 real radii, and the upper panel shows this fraction integrated between 0.2 and 1 real radii. So in the very center, after 3 to 4 times 10 to 11, you start having more hot gas. But in the outskirts, filaments can still survive and bring this cold material deep into the halo, even to several times 10 to 12, perhaps even 10 to 13 solar masses. The higher energy you go, more likely you have this cold filament surviving. So, so what happens then in these halos? Well, after, let's say 5 times 10 to 11, details depend on metallicity and the baryon fraction of the halo. The halos contain mostly virialized shock-heated gas. And the regions that are infalling through the cold, dense filaments have much lower cooling time than the rest of the halo. So they have much smaller chance to have a stable shock that would kind of support it in that region. The filaments can still go deep in and bring the supply of gas very close to the galaxy, perhaps even connect to galaxy, depending on the details that I will again discuss in a second. So we have this mixed scenario where some of the hot gas will clearly cool in the central regions if it has a high enough density and shorter cooling times, but you're also pumping the cold gas very close to the center of the halo. Finally, with the even later times, at redshift of 1 or below, you tend to disrupt fully the filamentary infall in the very center. And in halos like the Milky Way or slightly higher mass, we tend to be dominated by the cooling of the hot material in the central regions. Again, in the outskirts, you might still bring some of the lower entropy and lower temperature gas deeper in, but in the very center, typically it's going to be the cooling of the hot stuff that will give a supply of gas. The issue here is not fully closed. There are all kinds of tests to this scenario being done from all sides, which is great. And the results are still not fully conclusive which way things go when you put in the feedback, whether you destroy the infall or enhance the infall. When you increase resolution, there were some suggestions that you might disrupt certain filamentary regions, but the recent work with increased resolution showed that you might actually enhance filaments. This is an example from Beden and Shiachki, the recent paper from last year, where they increased their base simulation of a massive several times 10 to 12 solar mass halo at redshift 6. When the gas is at high densities, so filaments can survive very deeply into the halo, even when they're surrounded by hot gas. They kept increasing resolution by about a factor of 512, especially focusing around the shocks. And they found very crazy results. Once you go to this extremely high resolution, their halo changes. The fraction of the hot gas drops dramatically. The number of filamentary infalling regions increases. The turbulence of the halo increases, providing extra support for the gas and so on. And the covering factor of this cold gas also increases. So we are working on this, but we are still not at the not resolving all the relevant scales, such as this droplet scale, for example, from McCord's work. So there is still some work to do, but we are learning more and more over time, and resolution definitely matters for the results. Some of the other issues that we've been worrying about in the community over time is that you have this cold gas streaming through the hot halo. It can be maybe destroyed at the end by a shock, but can it be destroyed also by hydrodynamical instabilities that occur during this motion? And again, there were different results depending on what physics you included. This is a recent results from Nir Mandelker. He actually gave a nice tutorial yesterday about this. And the punchline is that when you include cooling in this moving filament through the hot surrounding medium, you not only survive for much longer time during this motion, but you can actually increase the mass of the cold moving component through the mixing layers of the moving stream. So the picture roughly holds, but there are details that needs to be studied and are being studied at all times. However, most of the stuff I discussed so far was ignoring outflows from galaxies that occur at all times. And if we had only inflow in the universe without regulating it, we would produce galaxies that are way too massive. So this is an illustration actually from my own old work, where this black curve is the observed mass function of galaxies. The thick black curve is just the line I drew by hand, and that represents what would be the mass function if all the baryons cool in all the halos. And the red line is results from simulations that don't have outflows, but only have UV background as a only source of heating outside of gravitational heating. So you see that inflow forms galaxies that are way too massive, both at the high mass end and at the low mass end. At the high mass end, the problem is about factor of 2 or 3 to match same number density. At the low mass end, problem is orders of magnitude. If you want to match the same number of density, you need to decrease the mass of galaxies by a factor of 100 or even more. So we know that gas needs to be expelled from the galaxies, or somehow accretion needs to be prevented. And in the low mass end, it's most likely done by some sort of stellar feedback. And at the high mass end, the most commonly invoked candidate is the AGN feedback. So I will focus mostly at the lower mass galaxies from Milky Way and below. And we did discuss potential gas inflow through halo condensation in a week 1 or 2. So we did discuss this high mass end in much more detail. So we'll focus now in the lower mass end. And just the general conclusion about inflow and outflows. So inflow fuels both, because you need fuel first to form stars and then to eject the material from galaxies. So you really need to model both of these processes. Doesn't matter if you're studying gas going out or in, you have to take into account for both. And you need to figure out what is their interaction in the halo. And there is more and more work done on this, both from the large scale cosmological simulations that have relatively crude realization of outflow, where you prescribe what your outflow will be doing close to the galaxy, and then you let it do its damage further out. But they have really good statistics, so you can see all kinds of scenarios that can happen there. And it's been also looked at from the zoom-in type of simulations like FIRE that in many cases have actually very detailed accounting for cell-consistent generation of bursty outflow from galaxies. So your subgrid scale is kind of around a few parsecs in the star-forming region, and then you try to put our understanding of stellar population and see if you can generate the outflow from the galaxy. And these can provide more details, but statistics are very limited, so we kind of have to play with both. All right, so here are some examples of what might be going on when inflow and outflow interact. This is the results from the relatively old now FIRE simulations from Sasha Murato. And first of all, we find that star formation in the low mass galaxies at high redshift. So this would be the really low mass halo at redshift 2. It's pretty bursty. The black line here shows star formation. The consequence of this bursty star formation are strong outflow from the galaxies, shown by these red lines. This is the outflow in inner halo with dashed and outer halo in dotted. And they're so strong and so mass loaded, they can actually damage the infalling gas. In the inner halo, you see that even the infall becomes more episodic. It's still more continuous than the star formation outflows, but strong outflow episodes tend to disrupt infall temporarily. But when you go close to the virial radius, infall is semi-continuous. So even these highly mass-loaded galactic winds don't do too much damage to the infall very far from the galaxy, but close to the galaxy, they can actually be disrupted. So this is shown in a little more details in this slide. So these are two different snapshots of a galactic halo. So this case is about 10 to the 11 solar masses at redshift 3. And this shows outflowing gas on the left and infalling gas on the right. And the velocity structure of the infalling and outflowing gas are shown on the leftmost panels here. And you can see that when these strong episodes of outflow happens in the very center of a highly star-bursting galaxy, you start damaging the infall very mildly in the center. Biggest damage comes when you kind of spread out through the halo, but you don't really disrupt the filaments in the outer halo. Very soon after, the hot gas might propagate further out to cold gas. It's either disrupted or rains back onto the galaxy, and the filaments just reestablish themselves and start providing fuel to the galaxy again. Something similar has been seen in large-scale simulations. This is results from Dylan Nelson from 2015. And you can also see that this outflow here might be disrupting filaments in the very inner halo, but on the other hand, might be also squeezing filaments in the very inner halo. So there's definitely some effect that we don't yet fully understand what it is, but the interaction needs to be taken into account. So what is important is that outflows affect infall two ways. First of all, you might just interact with the infalling gas and you might be ejected fuel outside of the galaxy. So that would be kind of ejective feedback, but they also prevent some of the infall globally over long time scales. So they have also preventative role. And this is kind of where small and large scale simulations agree that you not only eject material, you also prevent some of the further infall. So this is again example from Dylan in a few times 10 to 11 solar mass halo. And there are different lines showing feedback and no feedback simulation. And you see that when you look at actual rates of accretion, even the actual rate of accretion drops by around factor of 2 or 3 with respect to no feedback case. So it's not only that you ejected a lot of material, but you prevented some of the infall to come in. And finally, the infall and outflow interaction is needed to explain many observational trends. So again, it's not only that we need outflows to eject material from the galaxies, we need to do something to infalling region. This is an example from Claude André, where we added fire type of feedback in high resolution simulations at redshifts 2 to 4 of a progenitor of the Milky Way like halo. And here stellar feedback ejects some of the gas outside of the galaxy, but it also spreads out these infalling regions. So the filaments that are well defined are now much thicker infalling region in which small satellite galaxies can blow strong winds. And this kind of interaction is needed to explain observable, in this case, statistics of Lyman limit systems covering Lyman Bray galaxies. All right, so what does this mean? Well, this means that also the material that will be coming back at certain time will not be primordial. So the streams and infalling material at high redshift might as well just come from unpolluted intergalactic medium, but later times, especially closer to redshift 0, lots of the infalling material will come from already recycled gas. This is illustration from Ben Oppenheimer, and it shows that fraction of material that's being accreted at late time galaxies, especially at high masses, this is this green line, has come from the previously ejected material. So the fraction of primordial gas, in this case, dominated in low mass halos, but in high mass halos, it's all been in a galaxy at some point of time. It's being rejected, mixed in with the rest, and then it's raining back onto the galaxy. And this fraction tend to be important at late times. This is from Daniel Angles Alcazar for two different mass halos. On the left is 10 to 11 solar mass halo. On the right extend to the 12 solar mass halo. And this just illustrates that when you are at redshift 2 to 5, roughly, then you're dominated by this region, this color, which is fresh accretion from the intergalactic medium. So this is the material that's kind of coming in for the first time. After a redshift of 2 or 3, you start having a pretty important channel, which is this lighter color part here, which is recycling of your own winds. So your blowing winds, they go sometimes to virial radius, sometimes to half of virial radius, but they're raining back onto the galaxy. So your infall has a significant component from those. But then at late times, going towards redshift 0, you might also get this crazier components such as intergalactic transfer. So the galaxies nearby, or the ones that were falling onto your galaxy, blow a lot of wind material, and now your galaxy is accreting that material. So it's pretty complex picture of what exactly galaxy is getting at late times. And as a consequence, metals that are being ejected initially tend to pollute the infalling gas as well. So this seems like a busy plot, but I'll just guide you quickly through it. So on the left is metallicity of the outflows, and on the right is metallicity of the infall from a sample of simulations with high-resolution simulations with fire feedback. And this metallicity has been scaled to the metallicity of the interstellar medium of the galaxy. So dwarfs have very low metallicities, but their outflows basically just eject typical ISM stuff out. When you compare it to the infall in a quarter of the virial radius, you see that the infall might have a little bit less metal on average, but it's very similar to what has been outflowing from the galaxy. It's also similar metallicity to the interstellar medium. In very low mass dwarfs, it can be lower by factors of few, but because most of the accretion is reaccreted winds, then you expect that these metallicities won't be that different. But then you go to higher radii, when you go to virial radius, now the differences are more significant, especially when you're focusing at this higher redshift bin, redshift 2 to 4, outflows, even at virial radius, has a metallicity similar to the ISM. But infall, because it's mixed with more of this primordial gas, has much lower metallicity, factor of 5 or even lower. So further from the galaxy, metallicity might be an indicator where you're flowing in and out. Closer to the galaxy, you might pull up some higher order statistics, but it might be more difficult. All right, so let's now go towards lower redshift, where the situation is a little bit different. So high redshift, we have strong infalling streams feeding the galaxy with high rates. We have bursty outflows and complicated infall-outflow region, but that at late times, situation kind of calms down. Star formation becomes more continuous, and outflows are not as strong anymore, at least in these simulations like the ones we have in FIRE project. And this scenario enables formation of thin disks. You're not destroying disk anymore. You're not ejecting highly mass-loaded winds, so material can come down and form low dispersion disk. In this case, star formation is roughly steady. Infall is also roughly continuous, both at the virial radius and in the inner halo. And it just nicely supplies whatever is going on with galaxy over long time scales, over billions of years. The steady infall now likely comes from the actual cooling flow in the Milky Way mass halos that were discussed by Jonathan yesterday at the tutorial. So we have a halo that nicely, slowly cools and just supplies galaxy. And that actually makes our studies maybe a little bit easier in some sense, and we can start looking into finer details of how gas actually joins the galaxy. I just wanted to point out that even though there is a cooling flow in the center, this is not fully isotropic situation. There can still be some preferential direction where the gas starts finally cooling out, or it may even condense from the hot phase in the inner regions of the halo. So this is the sample from analysis by Largescale, and I'm just showing lower entropy gas coming from a couple of preferred direction at late times. So some of these infall might still appear kind of filamentary, but it's not necessarily directly connected to the cold filaments that exist in the intergalactic medium. All right, so this is roughly how things work in the standard case of having hydrodynamics and the stellar feedback from the standard sources. But lately we've been discussing a lot potential non-thermal sources of feedback that can actually change the outcome for the gas infall, especially at late times. So I'm just gonna, in a few slides, briefly discuss this alternative scenario of what might happen with a late time infall. And the reason why this might be interesting is that a couple of observational constraints indicate that cosmic rays might need to escape galaxies. And if they do and manage to couple to the surrounding CGM, they can provide non-thermal support for halo gas so that we don't have to support gas just with high temperature. So in a simple model where we implemented observationally motivated transport parameters for cosmic rays, these cosmic rays can actually do extreme change to the Milky Way mass halos and prevent a large fraction of the hot gas to be there in the first place. So what they do, they change the density of the halo and they slow down the infalling material, and the conditions are such that you can completely avoid the virial shock in these mass halos. Now, I wanted to point out that when you go to even higher masses, we are likely to get back to the standard picture because star formation typically dies down. The sources of cosmic rays might not be there. The depth of potential veil is higher. And I also wanted to point out that this is strictly at low redshift. Typical non-thermal pressure from cosmic rays in these simulations is not dominant at high redshift galaxies. So this is a potential alternative scenario for the Milky Way mass halos at late times. And the consequences of skipping the virial shock are very dramatic. So instead of having these clear shocks around the virial radius and occasionally a lower temperature gas penetrating to some depth and then being dominated by the hot gas deeper in, you are now completely dominated by this warm gas by 10 to 100,000 degrees. And some mild shock might exist this far away, but they're not really affecting what's going on in the inner halo. The other consequence is that the cosmic ray pressure gradient can start pushing the gas slowly, and you might form these weak winds that might not be launched straight from the galaxy, but roughly few or even 10 kiloparsecs from the disk. You might start pushing material with tens of kilometers per second outward. And that means that the infall that was already typically aligned roughly with the galactic plane now is going to be even much more aligned because you're kind of not allowed it to exist so much in a vertical direction. And the rough consequences for the infalling part, which are illustrated here. First of all, this scenario decreases the star formation rate of galaxies at late time. So you have colder gas, but you're holding it with non-thermal pressure. So you're actually not getting so much supply and your star formation rate drops. The second of all, when you look at the infalling and outflowing gas, they're completely changed. First of all, outflow is much higher, especially far away from the galaxy. So these inner ones are any mini super bubbles that might push the material to maybe few or tens of kiloparsecs, but they don't go far. But far out, cosmic rays can actually push you much more strongly. And then the infall is typically can be a little bit higher further out, but it's typically much lower further in towards the galaxy because you're just not allowing the gas to form this cooling flow-like behavior like what we've seen before. So this is better illustrated here also with the velocity of the infalling and outflowing gas. So any kind of infalling gas will be also slower than it used to be. And also the outflowing gas tends to be pretty slow, only tens of kilometers per second. All right, so I'll come back to this picture and analyze it a little more, but the couple of questions that have been asked during this workshop were related to how does gas actually join the disk. So I wanted to go to there in the remaining time and discuss what might be happen with this accreted material once we zoom in onto the galaxy itself. We had this kind of funny suggestion in the old paper that it's possible that cold mode gas smoothly merges onto the galactic disk like a stream of car entering an expressway. That was kind of a sentence that Neil Katz came up with. We wanted to describe something that we call co-rotation today, but we didn't know in detail how to do it. So this is an example of the accreted material shown as green marked particles at a high redshift galaxy from this old work, where you see that the infalling gas is kind of turning and starting to join galaxy. This was analyzed in much more detail in Danovich with Avishai and others a few years ago, that they found something similar. First of all, they found that the infalling cold gas has factor of 2 to 3 higher angular momentum than the average dark matter halo. And then when they look at the streamlines of the gas, they see that gas is trying to align with the galaxy further out at these regions that is typically tens of kiloparsecs from the galaxy. And in some cases even forms a ring-like structure, especially at higher redshift. So the gas is trying to join the disk way outside of the disk. Somehow is aligning its angular momentum and trying to become part of this bigger structure. So what we see as a star-forming disk itself might be only a small part of the whole physics that happens there. The alignment might be happening much further out. And if you see gas at even tens of kiloparsecs from the galaxy, it might already show some sign of rotation. Well, the problem with these two works was in part that there were no really strong outflows. So for high redshift galaxies, it might be a little bit more problematic. You don't have as well-defined disk plane. The galaxies, especially at medium masses or even L star, might be more affected by velocity dispersion, and exact alignment is not that clear, but there was a sense of this co-rotation from the early work. So let's see how this works at low redshift when we see galaxies like the Milky Way or nearby one that we can probe with both absorption and also emission type of studies, for example, from H1. So let's talk about how gas might be accreted into galactic disk. So again, there are some examples. The one on the left is closer to redshift 0. The one on the right is around redshift 1, 1.5. It showed that whatever gas is infalling, in this case, it was a leftover of the cold mode and some of the cooling of the hot stuff as well. But in both cases, there was a clear sense of co-rotation that went out to 50 kiloparsecs or even more. So gas is already trying to align with the plane and trying to rotate similar way as the galaxy. And that's been seen in these two different simulations. And this is something that has been lately observed at low redshift, especially by Crystal Martin and Stephanie Ho and others. And also there's a nice work at high redshift by Nicolas Boucher and his group. I think they actually had a paper last night that I didn't have a chance to digest. So there is this general picture that gas is co-rotating and acting to the galaxy. And in a sense, this is just a statement that we didn't really have to have simulations to make, because if you want to build the outer disk that have high angular momentum, you kind of have to have gas that has that high angular momentum. I mean, otherwise you need to have much bigger reservoir and lose it very strongly to end up there. So to illustrate this angular momentum, here's an example from fire simulation. So these are 4 different Milky Way mass halos simulated with the fire 2 feedback and with different physics. So in the top row, these are pure hydro simulations of something that we call fire 2. In the medium row, we added MHD into the mix. And in the last row, we actually added cosmic rays. So the reason why I like cosmic rays is that they slow down star formation to be something that we observe. The Milky Way mass halos with cosmic rays have 2 to 3 solar masses a year, while without cosmic rays, they go to 5 to 10. So it's a little uncomfortable to actually look at the gas infall with pure hydro. But what you see here is that in the inner galaxy, we compare this angular momentum, specific angular momentum plots to the rotation curve of a galaxy shown in this red dashed line. In the inner galaxy, the gas is fully supported by rotation, so that's a normal disk. And that's kind of independent on the technique and the galaxy we use. And that continues to 10 or 15 kpc. So that's something we would call a galaxy. It's fully rotationally supported structure in which stars are forming. However, when you go outside of galaxy, there is a gas whose angular momentum is similar or even a little bit higher than the outer disk. So if anything from 20 to 50 kiloparsecs fall onto the galaxy, it's more likely going to join outer disk or somewhere in the outskirts than in the center, just because it has such a high angular momentum. It would have to lose huge fraction of its existing angular momentum to settle deeper in. So what I wanted to say with this plot is that you can have the hot halo in the center, like you do in hydro, or you can have this warm, non-thermally supported material like you have in cosmic ray case. In both cases, the material in the inner few tens of kiloparsecs have angular momentum comparable or higher to the outer disk. So once they settle, it's more likely going to be settling somewhere in the outer disk. All right, so now I'm going to focus mostly on these cosmic rays halos, largely for the fact that their star formation rates are closer to what is observed, and some of these results apply to hydrons as well, but typical rates and velocities are higher in hydrons. So because of this co-rotation of the inner halo, we expect things to settle pretty close to the disk. And now I just improved the same angular momentum plot by adding this blue line that shows infalling gas only. So this is the gas that is going to soon join galaxy. So you see that gas that joins the galaxy has a similar angular momentum as the rest of inner halo. On average, it might be actually slightly lower, but still similar or higher than the disk edge, so that the edge of the material is being accreted. So now you see that we measure these things in these funny units. These are now in RDLA radius. So we define disk as being the material whose column density is higher than the DLA column density. And what you can actually also see here is that almost perfectly captures where do we get to this co-rotation. So for the zeroth order, we can just say that edges of the disk are where we drop below DLA density. The second thing you see here in this plot is that the gas is not only having similar angular momentum, but it's well aligned with the disk plane. Of course, in the galaxy, alignment is close to perfect. It's within a few percent. But when you even go to a couple of these DLA radii, this DLA radius is roughly 15 kpc or 20, depending on the galaxy, you still see this alignment to 80, 90%. So the gas is not sitting perfectly in a disk. It's kind of flare up or funnel-like structure that is trying to infall onto the outer edge. And now we can zoom in onto the kinematic profile and mass flux rates from this material. And on the top panels here, I show two examples of Milky Way mass galaxies. And you can see that when you're at about 1.5 or 2 RDLA, which again, it's about 30, 40 kpc, the gas is radially falling in with about 20 kilometers per second. So most of the infall won't be easily seen if you want to find high velocity clouds or things like that. There will be a fraction, but that might be subdominant. So the infalling material, even tens of kpc from the galaxy, it's pretty slow. It's only tens of kilometers per second. And then it slows down radially, but from angular momentum, we know that it co-rotates closer and closer and closer. And it reaches almost full co-rotation somewhere between 0.5 and 1 RDLA. After that point, the gas just sits in the galaxy. That's where it ended, but it doesn't sit still. You can see that systematically there is this tiny little motion of like typically 1 to 3 kilometers per second. And I'll come back to this motion. Those are actually radial flows of the material within the galaxies like the Milky Way themselves. And typical accretion rates are of order of few solar masses. But both to find these velocities and to find accretion rates, you have to do large statistics. So in this case, we average it over, I think, tens of snapshots of the galaxy, because at any given time, you might even see gas outflowing. But when you average it over long timescales, over hundreds of million years, there is a general inflow signal that you can pick up. So if you look at any individual galaxy, you might not see a picture like this because of this very large dispersion. But adding many, many objects, you might pick up the signal that we see in these simulations. All right, so I'm just gonna show a few more details about it before I summarize. And we had a lot of discussion about what is actually happening with this inflow, whether it's parallel to the disk plane or vertical. And in these fire simulations with cosmic rays, and also without cosmic rays, but to a different degree, the mass flux is mostly parallel to the disk, but again, with large variation, shown with these dashed lines here. The orthogonal accretion, it's very low. Sometimes you might get some, but in many cases, it's actually net outflow if you have averaging over time. And we selected a subset of accreting particles randomly just to illustrate what's going on. So again, these are 4 different Milky Way mass halos. This square, the rectangular shape here represents disk with the height of 2 scale heights of the gas and the extent of 1 DLA radius. And the particles here are followed for 1 orbital time at the disk edge, so typically like half a gigayear or so before the accretion. They're color coded by the radius where they join, with this bluish color meaning the edge, and this kind of reddish colors meaning the center. So you see the particles are already aligning close to the disk plane, but not perfectly when they're far away. They approach the disk. When they are very close to the disk, they tend to settle into full rotation and fully join the disk roughly at 0.7, 0.8, or 1 RDLA. In the more compact cases, in the more compact disks, so these are all similar mass, but different disk sizes, some of the settling might occur deeper in the center, and the angles with which they settle might be higher. In this particular case on the left, this is actually a galaxy that just had a merger at redshift point 2. You see that the accretion is all coming from one direction, so there is still tidal leftover of what's being accreted onto the galaxy. All right, so that's roughly the picture. So the gas is not perfectly aligned with the disk. There is definitely a spread there, but there is a global sense of rotation, and the way angular momentum works, as you approach the disk, you just need to lose very little, and you're going to settle in the disk edge. So the question is then, how do we supply the star-forming regions in the very center? And that's the question we had in this conference a couple of times. If you're settling always at the edges, how do you get in? At high redshift, the situation might be more dramatic because there is like much more violent dynamics happening with the gas. But the delay times is actually this slow radial inflow of a few kilometers per second that I indicated in the plot a couple of slides ago. And so we wanted to see if we have enough supply to kind of fuel star formation in the very center. And I'm just going to mention that these galaxies, again, those are the 4 Milky Way mass galaxies, they have distribution of star formation activity that is different as a function of radius. And the ones that seem to be more spread out with the radius, they have different rates of radial inflow when we measure them deeper in versus outside. The ones that tend to be more concentrated, like this M12b, they have similar radial inflow throughout because all of the star formation happens close to the center. So for this case, if you measure radial inflow rate, there are typically few solar masses a year. And as star formation depletes the inflowing gas, then these rates drop further and further because smaller fraction of that star formation rate happens in the inner galaxy. if star formation is centrally concentrated, throughout the disk, you can see the rates of infall that it's comparable to the star formation rate of this galaxy. Again, the one on the left here is a kind of still ongoing merger, so it has a little bit crazy mass flow rates and also dynamics. I wanted to point out that to pick up the signal, I guess observational colleagues can tell us if that's possible or not, but you definitely need to average out the flow of galaxies radially in radial rings, and also you need to average out this flow of gas over time. So this is just a snapshot at any given time, color-coded by radial velocity within the disk plane of the gas for those 4 cases. So the densest material moves with only a few kilometers per second, but there are these regions that are moved around by 10 or 20 or so kilometers per second throughout the disk. So if you take any galaxy at any given time, it might be hard to pick up this few kilometers per second radial infall, but if you have large statistics of galaxies, there might be a way to tease out this information and get typical radial flow rates of galaxies over time. All right, so I have additional maybe 30, 40 slides that people can ask about later, but to enable more time for discussion, I'm just going to go to summary and summarize basically what I just said. So we found that the gas infall is dominated by efficient filamentary cold mode accretion at high redshift and cooling of the hot gas at late times. Feedback clearly affects properties of the infall. Details are not yet clear. Several groups are doing studies as we speak, but we don't have extremely clear picture of how and when we disrupt filaments and how long is this disruption lasting, and exactly how is this preventative feedback working. And the resolution convergence is still unclear. This resolution convergence is especially important once you have cold stuff mixed in a hot medium. As we've seen in the first few weeks, this is a still open question, even with ideal simulations that are trying to get to the nitty-gritty of what might be going on with mixing layers. So it's no surprising that in the large-scale cosmological simulations, even zooming cosmological simulations, we don't have a fully convergent picture of what's going on. Thing to keep in mind is that late-time infall often comes from large-scale recycling, not always. And higher redshift you go, you're less likely to get into this recycled component. But at late times, the gas infall close to the galaxy might have similar metallicity to the outflowing material, and it can be similar to the general ISM, but again, not all of it. And we should worry more about these non-thermal processes such as cosmic rays, because even if this is extreme case and super simplified transport, they have potential to completely change the phase structure of the late time infall, even if they don't change that crazily kinematics close to galaxy. So we need to observationally constrain these non-thermal processes to be able to more cleanly study infalling and outflowing gas. And this is something that seemed to be a consensus view from many different simulations, that when the gas approaches galaxy, it corrotates with the disk and it creates close to this outskirts. That doesn't mean that the fountains are not also picking up some gas. It just, in these simulations, there doesn't seem to be need to explain current star formation, but might be an issue of resolving these fountains. And there is a way to transport the gas that is being accreted to the outskirts, to the star forming regions in the inner galaxy. And this is through radial flows through the disk. And we are kind of working hard to understand exactly what's being torqued and how it's being torqued via these mild radial flows over time. So I'll stop here. Thanks.
Well, thank you very much. I will applaud live.
Thanks.
So people can use applause icons. Thank you for a very insightful talk, and particularly how you connected a number of the things people have already discussed in this conference to what you see in those simulations. It is now almost 3 minutes after the hour. And so I want to give people a 5-minute break and reconvene at 8 minutes after the hour, where we will have a panel discussion.